There's an ancient legend told in 1,000 different ways across 1,000 years. A wise man presents a king with a gift, a game of such elegant complexity that the king is enchanted. "Name your reward," the king declares. The wise man smiles. "Just rice, your majesty. 1 grain on the first square, 2 on the second, 4 on the third, and so on, doubling each square until the board is filled." The king laughs. "Such a modest request, but let's count together. Square 10, 1,000 grains, a handful. Square 20, 1,000,000, a large sack. 1,000,000,000, a warehouse. Square 40, 1,000,000,000,000, every grain on earth." And by square 64, 18 quintillion, 446 quadrillion grains. More rice than has ever been harvested in the entire history of human civilization. But why is doubling so powerful? Let's see the difference. With simple addition, 2, 4, 6, 8, it grows steadily, predictably. But with doubling, 2, 4, 8, 16, 32, watch what happens. By square 10, linear gives us 20 grains. Exponential, over 1,000. This is the formula, 2 to the power of n minus 1, the mathematics of exponential growth. So what does 18 quintillion grains actually look like? 210 billion tons, more than 1,000 years of global harvest, enough to cover the Earth, a pile taller than Mount Everest. Einstein called compound interest the 8th wonder of the world. It's the same math, the same explosive power that tricked the king. This simple board taught humanity about the power of exponential growth. But exponential growth is just the beginning. Chess hides even deeper mathematical secrets in the way pieces move. Consider the knight the most unusual piece in chess. It moves in an L shape, 2 squares in one direction, then 1 square perpendicular. Here's the puzzle. Can a knight visit every single square on the board exactly once without repeating? Watch as the knight traverses the board. Each square visited exactly once, forming a perfect path through all 64 squares. This pattern has a special name in mathematics, the Hamiltonian path. Imagine a network of points connected by lines. Mathematicians call this a graph. A Hamiltonian path visits every point exactly once. No point skipped, no point repeated. The chessboard is just a graph. 64 squares are points. Knight moves are the connections. And on our 8x8 chessboard, there are over 26 trillion different knights tours. Now consider the queen, the most powerful piece. She can move any direction, any distance. She attacks in 8 directions, making her incredibly dangerous. The challenge: can you place 8 queens on the board so that none of them attack each other? It seems impossible, but watch. 8 queens, and not a single one can attack another. This is one of 92 possible solutions. This problem teaches computers how to search using a technique called backtracking. The knight's tour is graph theory. 8 queens is search algorithms. Chess patterns are the foundation of computer science. Every chess game begins the same way, but quickly branches into infinite possibilities. From the starting position, White has 20 possible first moves, 20 different branches, each leading to a different game. After White moves, Black also has 20 responses. That's 400 possible positions after just one move each. In a typical position, there are about 35 legal moves. This is called the branching factor. In 1950, mathematician Claude Shannon, the father of information theory, asked a profound question. How many possible chess games can ever be played? He estimated 35 legal moves per position and about 80 moves in an average game. 35 to the power of 80. That equals 10 to the power of 120. This became known as the Shannon number. Let's put this number in perspective. The observable universe contains about 10 to the 80 atoms, every star, every planet, every grain of sand. Possible chess games? 10 to the 120. Chess has 10 to the 40 times more possible games than atoms in the entire universe. If every atom contained another universe with its own atoms, you still couldn't count all possible chess games. Within 10 to the 120 possible games, certain geometric patterns emerge. Patterns that trap a king. Checkmate is pure geometry. The king's escape routes must equal 0. The back rank mate, pawns block the king's escape. The rook delivers checkmate. The smothered mate, where the king is suffocated by its own army. The knight's L-shaped attack, combined with the king's own pieces, creates a perfect geometric trap. So can a machine ever master this infinite game? Computers use the minimax algorithm, a brilliant mathematical strategy. The idea is simple. Look ahead several moves, then work backwards. Your opponent picks the worst option for you. You pick the best of those. This is minimax. But how does a computer score a position? Through the evaluation function. Material values, positional factors, pawn structure, all combined into a single number. In 1997, IBM's Deep Blue faced world champion Garry Kasparov. Deep Blue could evaluate 200 million positions per second. Pure computational brute force. For the first time in history, machine defeated the world champion. Mathematics had conquered human intuition. But in 2017, AlphaZero changed everything. It was never taught how to play. It learned by playing against itself, and in just 4 hours became the strongest chess player ever. Let's see an example. In its match against Stockfish, the world's strongest engine, AlphaZero played a move that no human would consider, knight to h5. A knight on the edge of the board. Conventional wisdom says that's bad. But AlphaZero saw something deeper. AlphaZero went on to win, playing chess like no one had ever seen before. Intuition, learned from pure mathematics. From the Rice legend to neural networks, chess has always been a window into mathematics. 64 squares, infinite mathematics. The game that taught computers how to think. The hidden mathematics of chess.